All right. So welcome, I guess, to the special lecture on cloud computing. Since both Professor Grant and Anshul are in Barcelona, so I will be taking this one. All right. So quite a few people, I guess, compared to how many are registered. Anyway, so a little bit about me. So I did my bachelor's in computer science and master's in mathematics from BITS Pilani in India in 2017, and completed my master's from informatics from TUM in April, and doing my PhD since July 2020 at TUM. So just started my third year. And so I'm mostly working on designing systems for ML using function as a service and extending FaaS to heterogeneous computing. I think Anshul described that in the last lecture. And also working on performance optimization and analysis across the FaaS stack. And also a little bit on edge computing, where we are looking on inferencing of deep neural networks on heterogeneous edge devices, and also orchestration of those workloads. Right. So more about me you can look at my website, or if you want, and if you're interested in what we are doing as a chair or what I'm doing, then feel free to reach out by email, right? And also some thesis topics if you're interested. Cool. This lecture, basically what we will talk about first, background on serverless computing, Kubernetes, right? And what the container ecosystem actually is. And are containers actually really secure? And then we'll focus on some of the solutions, right, out there for, I would say, like secure runtimes, essentially, right? So, or sandboxes, for example, Gvisor, Firecracker, Kata, and WebAssembly. So how many of you have heard about WebAssembly here? Any idea? Yeah, that's great. So then we will focus on Knative, right? And hopefully, if everything works out, then I have a demo planned. Let's see how that goes. All right. So when you talk about serverless computing, right? So if you look at the X and Y axis, so we focus on business and application logic on the x-axis, and the virtualization stack, right? What is the level of virtualization on the y-axis? So at the beginning, there was bare metal, right? So where everything was scaled based on physical servers, right? And they were deployed they were deployed for hours or days and essentially lived for years. Then we moved to infrastructure as a service, right? Where this whole virtualization was introduced, right? Using for essentially KVM, right? So you could spawn a virtual machine on the cloud in minutes, and depending upon your use case, it can last however long as you want it. Then we moved to platform as a service, right? So essentially application engines from different cloud providers, where we focused on containers mostly, right? And where deployment took essentially seconds, and it could last for minutes or hours. Right, so all of these are essentially server-based. And then in 2014, with AWS Lambda, they introduced the new concept of serverless, where you can essentially execute functions which could be started in milliseconds or seconds, and they can range, right? So the execution time can range from milliseconds to hours, essentially, depending upon what your use case is, right? But the idea is that all resource management was abstracted away from the user, and everything is handled by the cloud service provider for you, right? So if you look at what the platforms are out there, right? So there are essentially two divisions, I would call them, right? So there are function as a service platforms and container as a service platform, which are also serverless, right? So in terms of commercial, they are AWS Lambda, right? And the container as a service offering is Fargate. And for Google, it's Google Cloud Functions and Google Cloud Run. Azure Functions by Microsoft, and Scaleway Functions. Anyone heard about Scaleway? So it's a European compute cloud company, which is, I think, gaining traction. Yes?
I just wanted to ask, you didn't upload the slides yet, right?
Oh yeah, I will upload it after. Yeah. All right. So if you look at open source platforms, right? So there is OpenWhisk, originally started by IBM. Then OpenFaaS, it's a really cool project, and then FN, which is like a container native cloud agnostic serverless platform, they call it. So Oracle also started their cloud infrastructure recently, and their offering, Oracle Cloud Functions, is essentially powered by FN, the FN project, right? And Knative, which is, I think, one of the most popular ones, and is currently used both in Google Cloud Functions and Google Cloud Run. And we have this Fission project, which is also Kubernetes native open source serverless platform. And Kubeless was started by VMware, but it's actually deprecated now, so they don't want to pursue it anymore, right? Yeah, so in this lecture, we'll mostly focus on Knative. All right, so some of the advantages of FaaS, right? As I said, so you don't need to do any resource provisioning, right? Everything is done by the cloud provider. And there is on-demand auto-scaling, right, of the function instances depending upon how many requests are incoming. And then there is fine-grained billing. So you only pay for what you use and your compute time, right? And you can pack your servers essentially with as many function instances as you want, right? So and have high density essentially. Yeah, disadvantages. So it's mostly stateless, right? So for maintaining any state, you have to do external transactions with databases, right? And there's also a large amount of performance variations because everything is kind of like a black box, right? So where the actual functions are launched, no one actually knows. So the architecture of the processor where it is actually being executed can vary, and then the performance also varies. And it's not really suitable for compute-intensive workloads like longer-running workloads, because in that case, micro VM offerings would be more cheaper. And also there is limited security, right? So you have untrusted code running, and it's like multi-tenant. So one server is running multi-tenant workloads, so there's definitely a lot of security risk. So this is an example of, for example, how billing is done. I'm not sure if you're aware from Google Cloud, right? So essentially what you do is you allocate a particular amount of memory to a function, and depending upon that, you get certain number of vCPUs, right? Which is, I would say, kind of like number of cores, let's call it, right? So this is how it works for GCF. Interesting fact, like in one of our research papers, we found out that so the idea is that when you increase the memory, you get faster compute, right? But what Google was doing in their first generation functions is that even if you allocated 8 gigabytes of memory to your function, essentially what they gave you was only 4 gigabytes. So it was kind of a bug, which we found and reported to Google. So it's pretty interesting, I think, right? So there's also a lot of research about what's happening actually inside the cloud providers, like how they actually launch their functions and everything. Okay. So I think every one of you is familiar with Kubernetes, right? Okay. So this is on the left. You see the Kubernetes architecture, right? So it has several components. So from kubectl to etcd. Right, so kubectl is the command line interface through which you can interact basically with your cluster, right? And etcd is the key value database for storing all the cluster information. Then you have the controller manager for managing like life cycles, the scheduler for scheduling pods, and the API server, which is essentially your interface, right, through which everything interacts with. On the node, you have the kubeproxy for networking and the kubelet, which is the node level daemon, right? Managing the pods. And then you have the pods, which can be essentially a number of containers, right? And on the right side is just a better, I would say, enhanced picture of what happening in one node. So you have kubelet, you have CRI, and then you have the network proxy. So how many of you know what is a CRI in Kubernetes? Does anyone know? Great. So do you know what are the common CRI implementations in Kubernetes?
So the common ones are like Containerd.
Yeah.
And it's kind of based on, it's the same one that Docker is also based on, but Docker itself is not CRI compliant.
Yes, so do you know exactly? That's correct. And so how does Docker interface with Kubernetes then?
So up until the recent version, there was some kind of adapter. It was called the Docker Shims.
Yeah, exactly. Yeah, it was deprecated in 1.24. That's correct. And there's also CRIO, which is okay. There's also CRIO, which is a third runtime. So these are three populars, right? So Docker Shim, Containerd, and CRIO. So here we will focus on Containerd. Great. So let's go back to a basics a little bit. Containers and VMs, right? So what are containers, right? So I would say the basic idea behind containers is that they allow you to package your code, right? And give you a certain look at what the resources are on your system, right? Using, I would say, features provided by Linux kernel, which are called namespaces. So anyone knows how many privileged namespaces are there in Linux? Okay. So there are 5 privileged namespaces. And so network, PID, mount, UTS, IPC, right? And so C groups is for resource isolation of containers. So does anyone know if C groups is also a namespace? Okay, so it is also a namespace. And great, so that's the entire principle, right? So so you use Linux primitives, and then you share the Linux kernel between the container and what is running on the host. And the idea is that they have fast starts with minimal overheads and flexible isolation. So general question, if you want to find out what the namespaces are actually in Linux, can you find, does anyone know how to identify it? Yeah. So you can actually check the procfs file system, right? So whenever you launch a container, what the OS actually sees is just a process, right? And it has a specific PID, and then you can check the namespaces attached to that PID using procfs. All right, VMs. So also one more thing about containers, right? So what they also have is rule-based execution, right? So they have AppArmor and SC Linux, which allows you to, I would say, set policies, what your kernel can, what your container can interact with the Linux kernel. And there is also something called as seccomp BPF, which is secure computing in Linux using Berkeley packet filter. And then it allows you to filter the system calls, essentially, what your container can do with the Linux kernel, and then access to indirectly access to the hardware. So the only way I would say security is implemented is with containers is using seccomp BPF profiles, right? Okay. Then we move to virtual machines, which are a form of machine-based virtualization, right? And the entire principle is based upon kernel virtual machine. So any idea what KVM is? Yes, what is KVM?
It's a kernel module,
Yes.
which adds some hypervisor capabilities to the Linux kernel.
Yes. So it adds, it makes Linux type 1 hypervisor essentially, right? And then it already has all the components, right? For example, the resource manager, the scheduler, which allow you to then launch virtual machines. And then what the OS actually sees again is just a process. So each VM you launched after using KVM is a process. Essentially with their own virtualized hardware, right, and their own operating system, I mean kernel, which is the guest. Okay, and so it's essentially emulating hardware, and there are separation between the kernels, which is kind of secure, which is really secure as compared to containers, right? But there is obviously slow starts, right? Because you need to boot the entire kernel and then set up the hardware. So interestingly enough, there is another component which is called a virtual machine monitor, which sits between. So there's a hypervisor in between, right? So which sits between, which is like sitting between the virtual hardware and the KVM and responsible for managing all access to the hardware and also doing like special instructions, for example, interrupts. So everything like that is managed by the VMM. Okay, so container ecosystem, right? So as we mentioned already, so we have Kubernetes and the CRI, which defines an API through which you can essentially manage these container runtimes. So Docker was initially based on Containerd, right? And then they later open sourced the Containerd project themselves. So what essentially happens is, like, when you want to start a new container, a pod, for example, in Kubernetes, right? So then it interacts with the CRI, and then the CRI interacts with the container manager, right? So it's Containerd or CRIO, and then they use a specific container runtime, which is called, in most cases, it is runc, right, to start the container. So runc essentially forks a new process, which is your container. So it says here runc is implementation of the Oci spec. So what is Oci? Anyone knows? Okay. This is end of cloud lecture. So OCI is Open Container Initiative, right? So it defines a set of specifications of how your container images should be built and how the runtime should interact with these images. So if you want to create a new container runtime, it has to be OCI compliant, essentially, right, to fit within the standard. Okay, so what is Containerd? So Containerd is industry standard runtime and manager, and on Linux it is available as a daemon. So it's responsible for managing the entire life cycle of the container on the host system, right? And transferring of images, execution, and supervision, like in terms of when it exits and stuff. So also supports the complete OCI specification and supports snapshotting of containers. So where this is useful is you want to stop and save your state of your container to disk, and then if you want to, sorry. Sorry, hopefully it doesn't happen again. Right, so it supports snapshotting of containers. What the idea behind is that you can save your state of the container on disk, and then, for example, to save DRAM, and then if a new event comes up, for example, you can restart that container on event base, basically, and restore it in memory. And also, it supports running sandboxes through something called Shims. Right, so what is a shim, right? So essentially what happens between containerd and the runc is there's a component setting called shim, which is, it's also, it's a daemon, right? So it's like a software which resides between the runtime and between the manager and the runtime. And it's kind of a way to abstract low-level runtimes. For example, runc or runsc, and there are several others. So it defines an API through which you can implement. So containerd shim basically attaches itself to the container and lives as long as the container is alive, right? And so runc essentially has two modes of execution. One is foreground and one is detached. So in foreground, if you run a container, then runc will attach itself to the container process and then execute as long as the container is alive. In detached, basically, it will fork the container and then exit automatically. All right, and containerd shim is also responsible. So all the runtimes use the detached process in runc, like the detached mode. And the shim is also responsible for intercepting all the streams, right? For example, std in and out and error, and then redirect them to the container manager. For example, if you do kubectl logs or docker logs, right? So essentially what's happening is that they are being redirected by the container to the shim, and then you can see them on your shell. Also, if you do like docker exec -it, right? And you want to do an interactive session with the container you're starting, then everything is managed by the shim. Okay, so this is the containerd ecosystem, right? So it's increasingly popular, and mostly what we focus here on is the kubelet, the CRI, right? And DevMapper is essentially a file system, I would say, right, for transferring the image onto a guest OS. We'll talk about it later, right? But it's like you can say it's like a protocol. And then there are the low-level runtimes, right? So runc, we'll talk about Kata, we'll talk about Firecracker, Gvisor, and then there is definitely the shim, which enables implementation of these different runtimes. And the system can be anything, right? So it can be ARM, Intel, or Windows, right? Or Linux. I mean, the architecture can be anything. Depending upon the runtime, there is support, or some runtimes don't support ARM. And yeah, you can, Windows, I don't know, but Linux definitely everything works. So if you look at containers, we think they are safe, right? But actually, not really, right? So especially if you look in terms of the cloud service provider, right? So there is a need for more isolation, right? So if you look at the Linux kernel, which is essentially what is being used in offerings of most cloud service providers, it has around 27.8 million lines of code, right? And it is being like the number of lines are increasing every year. And it has around 319 system calls in x86 64, right? And so the idea is that you want to prevent, so there are a lot of bugs, right? Which, I mean, they are being fixed, but they can be certain exploits, right? Which identify some bugs in these APIs and get more privilege, right, and get access privilege and get access to the kernel, and then controls complete system control. So we want to prevent that, right? And especially, I mean, there's multi-tenant code running on the cloud service providers, like millions of people are running their code, and it can do anything. So essentially, there needs to be another layer of security. So I'm not a computer security researcher, but if you look in the research in this direction, right? So all of them are basically focusing on finding these different types of exploits, right, in the kernel, or different new technologies. So essentially, there are, I would say, 3 categories, right? So there are system API type of exploits, where you essentially identify these APIs, through which you can get access to the kernel, right? For example, the system calls from user space to the kernel space, or in hypervisors, where you have these traps and emulation, right? So through this, you can interact with the system. So you try to exploit these system calls, and then find bugs and gain more privilege. So this is one type of attack which is commonly used. And there is another one, which is system application binary interface, right? Where essentially what you try to do is you try to find exploits in how the execution path of like whatever you are trying to run. So you run something, and you know that this components will be executed after that, and then you try to find bugs in the flow, essentially. And there is another thing called as side channel attacks, right? And here you try to exploit using some external factors, not related to the software or the code. For example, there is an attack which tries to uses the electromagnetic radiation emitted by computers to gain access to the hardware. So yeah, so these are different types of attack which are possible, right? But so the idea is that we want to minimize these attack vectors, right? So add more security and minimize them. So towards this, right, so there are different solutions, right, which have been proposed. So for example, for one of them is Gvisor, right? So it is an open source secure container runtime developed by Google, and it is completely written in Go. Any idea why they choose Go over C? Huh? Yes?
Because Go has a garbage collector itself, so it is quite easy to manage as well. And you can have the Go routines, which is like on top of the C. So that's why it's choosing this way.
Yes.
As far as I understand from the repository.
Yeah, so it's memory safe and type safe. That's correct. So that's why. And it is currently being used in production in Google Cloud Functions and Google Cloud Run. And also, I think also in the app engines, they're using it. So the essential principle behind developing Gvisor was that they wanted to minimize the system API attack vector, right? So they wanted to minimize the system calls, essentially, right? What the container or the untrusted code which is running has access to. So so what they do is they basically have a sandboxed host system API, right? They talk about how they do it, and what they implemented was using Go, completely separate, independent user space application kernel, right? And it also has support for Docker and Containerd. We'll talk about how it works there. And then it has 2 modes of execution. One is ptrace, and one is based on KVM. So in ptrace, it's essentially what happens is that you try to emulate the system calls, right? So it's actually not executing on the hardware, but they are being emulated. And then, so for example, you can launch Gvisor essentially on a virtual machine using ptrace, but you cannot launch it on a virtual machine with KVM unless nested virtualization is enabled. But then again, it leads to large amount of performance overhead, right? So ptrace anyways is not well suited for running anything because everything is emulated. Right. So it has really good support for x86-64 and also for preliminary support, I would say, for ARM. And yeah. So this is essentially the architecture of Gvisor, right? So we have this OCI compliant low-level runtime called runc, right? So essentially what you can do is instead of runc, which is by default used in containerd, you can plug and play, right? You can plug in runc, and then you tell your Kubernetes cluster kubectl apply, and start something with. We'll talk about how to do that, but start something with Gvisor, and then it automatically selects runc and launches your sandbox in that. So runc creates a sandbox, right, which has your user container and the sentry, which is this user space application kernel implemented in Go. So the idea is that all the system calls which are made by the user container are intercepted and processed by the sentry, right? So this is like the first layer of isolation, right? And then sentry also has to do some system calls with the host, right? So not all of them can be handled by itself. So, but in that case, they already know, like, so there are only like 10 to 20 system calls which they need to do from the sentry to the host kernel. So for that, they can filter it, right? So the second, by creating a seccomp BPF profile and allowing access to only those system calls, right? And so suppose that the container is exploited, right? So the user gets access to escalates the privilege and gains access to the system. He will still be inside the user space kernel, right? And he only still has access to a few system calls to the host. So this is how they essentially increase the security, right? So first level of isolation is the sentry, and the second level of isolation is the seccomp BPF profile. Also, they use a separate process called Gopher for anything related to network I/O, file I/O. So all file I/O or system I/O calls are transferred from the sentry to the Gopher, and they use this legacy protocol called 9P for doing that. It is not too fast, I would say, right? And so Gvisor is essentially not suited for running workloads if you want to do a lot of I/O, because 9P performance of 9P is not that good. All right, so yeah, so drawbacks, of course, right? So if you have a large number of networking workloads, right, or anything which writes to file for essentially, or I don't know, a lot of workloads which do a lot of system calls, then obviously it's not well suited, right? Because everything you would need to send to the sentry, and in some cases also redirected to the host Linux kernels, right? So as you already mentioned, that there are around 319 system calls in Linux kernel. So not all of them are obviously implemented in the sentry, right? So I think they implement around 220 or 211, something like this. So I mean, some workloads are not compatible with Gvisor. So what is also uses, right, for interfacing with containerd is the Shim v1 API. So this is not, I would say, high performant because what it does is that it creates a daemon for every container in a pod which is running. So suppose if your pod has 10 containers, it will create 10 containerd shims daemons attached to a single fork call in the by containerd, right? So which is not good. So then they, as an upgrade to this, there is a containerd shim v2 API, right? In that case, it only creates pods. Like it creates a daemon for one pod. So there's like 1-to-1 mapping. So it doesn't matter how many containers are within the pod. There will only be one containerd shim daemon running. So this is more scalable. So yeah, runc has issues with scalability as well. I mean Gvisor. Right. So then moving on to Firecracker. Right. So Firecracker sits between the Linux kernel KVM and basically a guest OS kernel, right? So what it is, it's a virtual machine monitor, right, based on KVM for managing these micro VMs, right, which are reduced implementations of the Linux kernel, I would say. And it is like designed from ground up, especially for serverless computing, right? Also, so Firecracker is an example of a virtual machine monitor. Anyone knows like a really famous virtual machine monitor for Linux? Okay, anyone heard of QEMU? Right, so yeah, so that's also VMM, right? Commonly used by most hypervisors. But the idea is that it is really bloated, right? So it has implementations for, I don't know, a lot of hardware features, different devices. And for serverless computing, you don't really need it, right? Because everything is kind of stateless. So yeah, it is implemented in Rust, which is, I would say, one of the most safest system programming languages, right? Minimalistic design, so they reduced everything, right? So no support for different types of I/O devices, minimal networking, right? And I think it has like 96% less lines of codes as compared to QEMU. So it has enhanced security and workload isolation as compared to VMs, because obviously, right, the amount of code that they have is reduced comparatively. So the attack surface with which the guest OS or the user container can interact with the hardware is reduced. And because of its minimalistic design, it has really fast boot of time and memory footprint, right? So I think normally they claim that you can launch around 150 micro VMs in 125 milliseconds per second, right? So it's pretty, I would say, optimized. Okay, and it is open source, right? So AWS wants to, I don't know, get help from the community essentially, right? So that they can improve it. And with respect to the container ecosystem, there is also there is definitely Firecracker containerd, right, and Kata containers, which we talk about later. But the problem with Firecracker containerd is that it is not CRI compliant, so you cannot interface with Kubernetes, right? So, but yeah, so there was this paper called vHive last year, published in ASPLOS. So essentially what they do is they implement a custom CRI which implements which interfaces Firecracker containerd with Kubernetes. So they were able to launch directly like functions essentially in Firecracker. And as already said, they are actually using the Firecracker in production in Lambda and their container as a service offering Fargate. Right. So how does actually the Firecracker VMM looks like, right? So so there are different components for. So it has like a RESTful API through which you can control what resources you want the micro VM to have, right? So the number, for example, the amount of memory or the number of CPUs, vCPUs. And there are also built-in rate limiters through which you can control the network and storage which the micro VMs are using for the entire host, I would say. And so metadata service is for sharing information between the guest OS and the host OS. And there is also this, so so the idea is same, right, across all sandboxes. So you have multiple layers of isolation. So one is the guest OS, definitely, and then there is this jailer component, which is kind of a sandbox. And similar to the seccom BPF used in Gvisor, right? So it also limits the number of system calls which the guest OS has access to. So I think currently only around 30 system calls are whitelisted. So from jailer to the host host kernel, right? So Kata containers, right? So they were actually at the very beginning started from by Intel actually. There was a project called Intel Clear Containers. So they were born from that. Currently, it's OpenStack Foundation project. So anyone know what is OpenStack? Great. It was also introduced in lecture, right?
Yeah.
From Professor Cardoso,
Yeah.
right? Great. So yeah. So it's an OpenStack Foundation project, and again, the idea is same, right? So you try to launch secure and isolated containers with a separate kernel. It is compliant with the Open Container Initiative standard, right? And so basically, again, the same thing. So you have Kubernetes, the CRI, and then it contacts with this Kata runtime, and then it launches essentially all of these components, right, for a particular user workload. So you have this cloud hypervisor, and then the guest kernel, which is running inside this micro VM, and a Kata agent, which is running in every pod, and then the user container. So obviously there can be multiple user containers within that micro VM, but there will only be one Kata agent running. So the agent this actually what we're talking about here is Kata containers version 2. There's also version 1, which is not that high performant, right? So the Kata agent in version 2 is implemented in Rust, and it's one per VM, as I already mentioned. And it is responsible for managing the user containers and also managing what they are actually running, right? So coordinating how they exit and everything. So managing all these input-output stuff. And this cloud hypervisor is essentially, again, a virtual machine monitor based on the Rust VMM project, right? And minimal design, right? Really lightweight, so no extra support for additional hardware devices, right? So reduced everything essentially. And in Kata version 2.0, they implement this container shim v2, right? So then you have only one shim daemon per pod, right? As I already explained, the difference between version 1 and version 2. Yeah, and the other interesting thing what they do is they support pulling container images directly in the VM. So normally what happens is that suppose you have, as well as with Firecracker, right? Suppose you have a micro VM, and now you want to run a particular user workload, right? So the host is responsible for downloading the container image, what will eventually run, and then that container image is exposed inside the micro VM using certain protocols, for example, VirtIO or VirtIO FS, right? But what Kata containers support is that the guest kernel, the pod, essentially can directly pull the image inside the pod. So there is, so the host doesn't need to be involved at all. So like the idea behind this is that they don't want to trust the cloud service provider anymore, right? So no trust. And then the host also cannot see anything which is running inside the micro VM. So it's like no trust policy, which is completely different from other solutions out there. So this is really interesting. Also, instead of Cloud Hypervisor, you can also configure Kata containers to actually start with KMU here. So that also works by default. So it's pretty configurable. All right, yeah, WebAssembly. So anyone knows why WebAssembly was developed? Okay, so a little bit of history, right? So so there is, so as you know, like most common language used in web browsers is JavaScript, and it's like universal, right? So what the problem with JavaScript is that it's not really high performant, and the web applications are becoming more demanding, right? So then there was this initiative by Mozilla in 2014, I think, called ASM.js, right, which tries to optimize subset of JavaScript code. Like they identify certain portions of JavaScript code which can be compiled ahead of time, right? So essentially what JavaScript does is that it runs inside a virtual machine and it's not really generating machine code. But with ASM.js, you could actually optimize certain parts of your JavaScript code and compile them ahead of time to generate native instructions. So you get high performance. That was the idea, right? So, but it essentially did not work out. And as a successor to this, right, all the companies from different web browsers, right, Google, Apple, Microsoft came together and decided upon the specification, which is essentially what we know as WebAssembly, right? So what it is, it's essentially a binary format, right? And they have this human readable representation, which is called WAT, which is WebAssembly text format, right? And so it is defines a virtual instruction set architecture, right? It has a set of instructions through which you can write WebAssembly, and it has a 32-bit memory space. So if it has a 32-bit memory space, what is the maximum amount of memory it can have?
4 gigabytes.
Exactly, yes. It has, so every WebAssembly module can have maximum of 4 gigabytes of memory, right? And this is, I don't know, so there's also a proposal for increasing it to 64 bit, but let's see. Currently work in progress. Right, so it is isolated from the host by default, right? We'll talk about how this isolation actually works, right? But that's the idea. So it's completely isolated. And it defines this system called as importing and exporting, right? So by default, a WebAssembly module, like, so if you compile something to WebAssembly, it's called a module. It does not have access to anything related to the system. By default, it's completely isolated. And then they have this import-export system through which you can give access to this module to the system. We'll talk about this in more later. So originally WebAssembly started out as being specifically meant for web browsers, but because essentially it is portable across operating systems, across different architectures, right? So it has also found use cases in different applications. For example, in serverless computing, it is actually really gaining traction. So there is this really good paper called FaaS, which was published in ATC 2020, which actually develops a serverless platform based on WebAssembly, right? And great. So then what? So out of the web, how would you run WebAssembly, right? So in the web, you can just run it with web browsers, for example, like the JIT engines, right, in web browsers, for example, SpiderMonkey, in Mozilla, right? So in Firefox. So they have this capability of directly running WebAssembly modules within them. But outside the browser, what you would need is like a compiler to compile to WebAssembly first, your application code, right? And then you need something called as an embedder to run it. So for example, if you want to compile C++, right, to WebAssembly. So currently the only support is from Clang, right? So you take Clang and then you generate LLVM IR, right? And which is then converted to WebAssembly. So it's like a target. So so on the right side, you see it on the right side. So you have a source, you generate LLVM IR and then through the IR you generate this WebAssembly module. Then the embedder takes that WebAssembly module and wherever it is running, it generates the LLVM IR from that and finally translates that to machine code. So if it is running on, for example, ARM-based system, so it will not be x86, of course, right? It will be ARC64 instructions, but the idea is that these instructions are generated to the machine code, right? So they are high performant.
So this embedder is like a different tool which also compiles it ahead of time, or?
I mean, there are different strategies for doing that. So you can also compile a WebAssembly module ahead of time, but there are also embedders which can do it just in time, right? So it depends. I think I have it in a couple of slides. Yeah. So module is essentially the application code compiled to WebAssembly, right? So it contains a set of functions, globals, your memory, which the module has access to, the import statements, export statements, and obviously the static data, right? So every module is instantiated by an embedder and is portable, right? So all WASM modules are portable. So example, if you have a binary which you get from compiling a C++ program, it's an ELF file, right, on Linux. So similarly, you can treat it like that. So WASM is equivalent to an ELF file. Okay, so now we come to the embedder part, right? So so there are several examples, right? So there's a lot of movement towards WebAssembly. So there's different standalone runtimes. So you can also call an embedder and runtime. So essentially the difference between them is how they execute the module, right? So there are embedders which just do like an interpreter. For example, how Python does it, right? So and there are embedders which do have JIT strategies, for example, WASM time, right? So they have just-in-time compilation engines for generating machine code using different compiler backends. Like, for example, they use LLVM, Clang, or there is this compiler based in Rust called CraneLift, right? So different strategies. AOT as well, right? So ahead of time you can compile it depending upon if you know what the architecture is, right? You can compile it and then directly run the compiled binary on that machine, right? So this import-export system, right? So if you want to import something, for example, suppose you have a system call where you want to read a particular file, right? So it would be a fd open, for example, right? And then it will show up as an import in WebAssembly. So the main function of the embedder is to provide implementations of these imports. So so embedder provides all these implementations, and without this implementation, the module cannot run. It also manages the memory space of that module, and by not portable, what I mean is that after you have generated the machine code, right, from the embedder, you cannot, so universality of the WASM module is essentially lost. And it's also possible for the embedder to actually link against what the native libraries are on the system. And as I already mentioned, that WebAssembly does not have any access to the host system, right? So essentially, if you consider systems, they are mostly, there's a standard, right? So it's called POSIX. There's no interface to do it by default in the original specification. So then everybody again came together and then came up with the specification called Oci, which is the WebAssembly system specification. And it kind of defines an interface of how you would interact with a POSIX-based system, right? So if you have standalone embedders, right, for example, Wasmtime, Wasmer, all of them implement this Oci specification so that your WebAssembly module can interact with the system. So how does it actually provide isolation, right? So there's a technique called a software fault isolation. So essentially what is happening is that the module is running inside the embedder. And as I already explained, everything is based on the import-export system, right? So you cannot really access anything outside the module without these implementations for import-export. So those are mostly saved and checked. So so that's why this is one point, like the import-export. Second is memory, right? So all Wasm modules have linear memory. So think of it as like this. So if you have a embedder, which is a 64-bit process, right? And all Wasm modules can have maximum 32 bits. So it's 4 gigabytes. So then WebAssembly embedder can launch multiple modules, right, which are 4 gigabytes inside its own memory space, right? So then it does not really need to allocate all that memory to like map it to physical memory, so it can be virtual memory, right? So suppose there is an out of bounds access by the WebAssembly module, right? Then it will essentially be a page fault, which will be handled by the embedder. So you cannot really access anything which is out of bound the memory space of the embedder, right? So that's why this is two ways in how SFI is implemented. In WebAssembly also there are other, I would say, parts of the specification through which you cannot really access arbitrary memory locations, right? So you cannot generate instructions through which to random addresses in WebAssembly. So it's anyways forbidden. So it also has control flow integrity, which like what it does is it enforces structured control flow. So I don't know if you looked into disassembly of C programs. So what happens is that suppose you have a function, right? So if you look at the disassembly, you will see that it's a jump to the first instruction of the function, right? Always. But in WebAssembly, so like a common exploit would be you would just change where the instruction is pointing to in C programs, right? But with WebAssembly, it actually, so since you cannot really write to arbitrary addresses, right? So you cannot generate random addresses in WebAssembly through its instructions. You cannot randomly jump to anything. Also, since the memory space of the module and the embedder is entirely separate, right? So you cannot really, I would say, change any of the instructions. So it's always enforces structured control flow of the program execution. So one thing which is lacking in WebAssembly is resource isolation, which is commonly implemented through C groups, right? So that is by default not available. So it's just a sandboxing environment, essentially, and it's a way of distributing applications. All right, so there is this really interesting project called Crustlet from, I think, originally started by Microsoft. So it allows you to run WebAssembly workloads natively on Kubernetes, right? So what they do is they implement this kubelet API, and then this Crustlet essentially runs as kubelet on your node. And so it accepts WASM32 WASI workloads. What it means is that when you compile any application to WebAssembly, you can specify what target you want to compile it to. Sorry. Does this happen commonly with other people?
Mm-hmm.
No?
Yeah, yesterday there was a lecture and saying so.
Okay. Yeah. Okay. So, what it means by WASM32 WASI is that you can specify that as a target, right? When you compile your application to Clang, and then it automatically generates the module which is compatible to that standard. And it uses WASM Time, which is like a big project from Bytecode Alliance, which is like a consortium of different companies which are trying to improve this the specification of WebAssembly, essentially, right? So there's also this really cool project called WASM to OCI, right? So when you run this Trustnet on your node, it is also responsible for pulling OCI compliant WebAssembly modules, right? So for example, how the Docker daemon would do it, right, for you when you try to run any container in Kubernetes. So this WASM to OCI project essentially allows you to set up a registry, right, which is for WASM modules, and then interact with that registry for pulling images. So it's mostly exactly similar to Docker Hub, obviously, right? So the size of WebAssembly modules is really small, right? So it's KBs as compared to container images, which is like MBs to gigabytes, right? So obviously it's smaller than Docker containers for sure. But I mean, the interaction is similar. All right, so this is like an example of how you could configure Containerd, right, to use all these different runtimes that we talk about, right? So the Containerd provides these plugins, essentially, right, through which you can configure different stuff. So, for example, for Gvisor, you could just use this runsc plugin and specify the runtime, right? And for Kata as well. So, as I already mentioned, right, that Firecracker Containerd is not CRI compliant, so I cannot directly use it in my Kubernetes cluster. So what we do normally is that you have Kata containers which allow you to actually create Firecracker, launch Firecracker and then create micro VMs using that. So that's why it's called Kata FC, because essentially in that case the low-level runtime that we are using for creating Firecracker instances is basically Kata, right? So important fact about when using Kata with FC, right? So you have to use this snapshotter plugin for interfacing and exposing the container image inside the micro VM, right? Because so Firecracker only supports block devices, and for that you need to use this devmapper snapshotter plugin for Kata, right? So this is how you would configure it. Right. So how does it actually translate to Kubernetes, right? So we have this CRI already configured. So how would you actually run it with Kubernetes? So Kubernetes provides these runtime classes, right? Essentially, through which you can basically plug and play and select whatever runtime you want to launch a container with, right? So so you would just essentially mention it here, right, as like an attribute in the YAML specification you write. So it can be Gvisor or Kata in our case, or Kata FC, right? Or you can also say runsc, which then it defaults to default. So by default, it always assumes run C if you don't mention it. So you have to install these runtime classes on your cluster, right? So there's just a specification you write. It's like 3-4 lines, and then it just works out of the box mostly. So pretty cool feature. And then yeah, let's talk about Knative a bit, right? So now I want to work with FaaS functions in Kubernetes, right? So by default there is no support, right? So in Kubernetes, so then Knative was developed, right? So it's like from IBM, Red Hat, and Google, right? So all three of them are essentially, mostly those are the three who are working on it. And it has 3 main components, right? Building, serving, and eventing. So building is for writing, using, it's essentially for CI/CD, but you can do it using Kubernetes. That's the idea, right? But anyways, it's deprecated, and there's a thing called as Tecton pipelines, like another project, which they are essentially using that for building, like using CI/CD. I mean, for CI/CD with Kubernetes, that's the project to go to. It's called Tecton. And this FaaS functionality is provided by the serving component, right? So whatever you think about serverless, that is done by Knative serving. And eventing is for defining DAGs, right? So in FaaS, you can also not only have a single function, but you can have workflows, right? So it can be acyclic graphs, right? One function calls multiple other functions synchronously or asynchronously. So if you want to have those kind of functionality, then you have to use Knative eventing, and then you can define source sinks, producer consumers, everything. Right, so here we only focus on Knative serving. Right, so it provides this scale to 0 and request driven functionality, right? So it essentially has 4 objects which are defined as custom resource definitions in Kubernetes, right? So after them, they are essentially first class citizens for KTest, and so they are service, route, configuration, and revisions, right? So what you actually do is like you deploy a service, right? And then it automatically creates a revision for the service, a configuration, and a route. And you can configure the route to basically say how much traffic you want a particular revision to go to, right? So a particular revision is essentially immutable and a copy of a configuration. So if you change the configuration, it creates a new revision, right? So that's pretty much it, I would say. It's quite simple to use. And yeah, so there, so default scaling in Knative is provided by this Knative pod autoscaler, KPA. So what it does is basically it scales the number of services. In this case, depending upon like number of concurrent requests that you want a particular service to handle, or the number of requests per second that you want to achieve, right? So you can configure that in your service specification, and then it automatically does that for you. But it's also possible to use horizontal pod autoscaler. What is horizontal pod autoscaler in Kubernetes? It was not taught, or? Okay, so HPA is basically used for, so also used for scaling, but you can configure so if you want to scale a pod with respect to a particular number of CPU consumption, for example. So you scale the pod as soon as the CPU consumption reaches 50%, or as soon as a memory reaches a certain limit, right? So that can be configured by HPA. So as I already mentioned, it is used in Google Cloud Run, IBM Code Engine, and Red Hat OpenShift. All right, so what actually is inside Knative service, right? So there are 2 containers. One is the user container, which we want to run, and then there is this queue container, which is automatically started and inject it into your user workload. So this queue container is essentially a reverse proxy to the user container, and then all the requests which are transferred from like when you to the service are first go through the queue container, right? So everything is first goes to the queue container and then is transferred to the user container. And it is responsible for collecting these metrics, which are essentially used for scaling the services, right? And Knative provides this command line utility called KN, through which you can actually really easily deploy services, check their status, and so anyways, since Knative is like first class citizen in Kubernetes, right? So you can actually use kubectl to deploy everything. So you don't actually need KN, you can just use kubectl, apply your specification, and it will automatically create a Knative service for you, right? For example, this is the YAML file. So anyone knows what is H2C? So H2C is HTTP2, right, for gRPC, or right. So normally, if you have all normal services are HTTP based, so if you don't specify H2C and the container port, then it will by default be HTTP and port number 80, right? So right. So this is how you write the specification, and there is a specific API available on GitHub through which you can look it up, right? The different options, essentially, what you can have. So this is how it works. Right, so that's the end. I don't know, so if we can have the demo. Anyone interested in seeing Firecracker being launched? Okay, let's try then. Let me stop the recording.